Previously, we talked about transfer functions and how we use them as a tool to represent systems. In general, in this course, we want to study four ways to describe a system. We start with ordinary differential equations. We assume that you know what ordinary differential equations are, and then we studied transfer functions. We learned that transfer functions are preferred because they're easier to work with in comparison to differential equations. They're easier to solve. Basically, they convert a differential equation into an algebraic equation, and that's what we are very interested in. The rest of the course, before we get to other subjects, we studied two additional ways to describe a system: block diagrams as well as state space representation. Okay, so block diagrams are something that, or a subject that was created to have, or mostly with attention to the physics of a system, and it has a good visual and graphical way to represent a system in comparison to other tools or other methods like transfer functions, state space representation, and differential equations that are more mathematical. So block diagrams represent the relationship of system variables by diagrams. The essence of block diagrams are blocks, obviously, that show a system or elements of a system, as well as these two very important tools. One of them is summation point, one of them is pickup point. So summation point is a way to represent when two signals or functions are being added, and basically, so here what comes out from the summation point is the addition of this signal and then subtraction of this signal. Pickoff point is when you already have a signal or a function and you are basically taking a sample of it. You're making a copy out of it. The blocks that we show systems with then can be simplified in these relationships. So if we have two blocks that are cascaded, for example, if I have G1 of S and G2 of S, I can write them down as G1 times G2. If I have a summation point, I can move it behind a block. Now, some people find it confusing when we say moving sum behind a block. They say, well, how come this is considered front, this is behind? That doesn't matter, to be honest. What is important, like nobody's gonna ask you, did you move the block behind the summation point or ahead of the summation point? What matters is what's happening here. You have a signal x1 and another signal x2. They were being added, and then their result was being fed to system G, and then that would create x3. Now, what happens if I want to move G here? So x1 is being fed to G, and then I want to do something that x3 remains this very x3. How can I create an equivalent model that has this summation block or summation point moved, and I have G on the left-hand side of it? Well, if I do that, I need to have block G to appear here too. So one way of thinking about it to create these equivalent forms is to start from a point, let's say x1, and then go to a destination, let's say x3, and then try to remember what you see on your way. So if I go from x1 to x3, the only block I see on my way is g. If I go from x2 to x3, the only block I see, again, is g. Now, if I want to create an equivalent form or model, I should still get the same thing. If I go from x1 to x3, I need to still see the same number of blocks or with the same content. So I need to see G. That's why I need to put a G here, because if I go from x2 to x3, I still need to have the same content. Let's see what happens if we move a pickoff point ahead of a block. So I have G here, and I want to move it to after the pickoff point. So if I move the block after the pickoff point, or basically if I move the pickoff point ahead of the block, what happens is that, well, I was going from x1 to x2 and I had G on my way. So now if I'm going from x1 to x2, I still need to have G. These are general rules of simplification of block diagrams. Here, if I go from this point to here, I have nothing. I have just 1 on my way. So now if I'm moving this G to the left, I need to add 1 over G to simplify each other. Okay. So we use these rules and we use these equivalent forms in more complicated block diagrams to simplify block diagrams. A very important, probably the most important one, is feedback. I recommend you to memorize this. If we have two blocks, G and H, where H is in feedback with G, the simplified form would be G divided by either 1 plus GH or 1 minus GH. The sign is the opposite of the sign I have in the feedback. So if I have a negative feedback, which is more common in this course, I have G, H, and then a negative feedback, I'm going to have G divided by 1 plus GH. If I have a positive feedback, I will have a negative sign here. In MATLAB, to define block diagrams, or to basically do the same thing that block diagrams do, you either can multiply. If two blocks are in series or cascaded, you just multiply their transfer functions. If they're in feedback, the command in MATLAB is just feedback. So feedback of 1 divided by s plus 1 and 2 divided by s plus 2 would create the negative loop, negative feedback loop of G and H. So the default is negative. If you don't mention the sign, MATLAB thinks you are putting these two blocks in negative feedback. Okay, so example, simplify the system in figure 2. I have G1, G2, and H. G1 and G2 are cascaded, and H is in feedback. So here we do signal analysis to show you what happens. So let's call this signal E, and then E of S would be R of S minus, so look at this, E is R minus H times Y. So this signal is Y of S. When it goes to H, the signal here would be Y times H. So E is R minus Y times H. On the other hand, we know that Y of S is G2 times Z. So Y of S is G2 times Z, right? So if I substitute Z, then Z is G1E. So Y of S would be G2 times Z. Z is G1 times E. So Y is G1 times G2 times E, right? So basically what I'm trying to do here is I'm trying to show you that the simplifications in the previous slide can be obtained by doing signal analysis. Okay, now if I combine these, I have y equals to G2, G1, E, but E is defined here. I substitute, I have G2, G1, R minus HY. I simplify and then bring this term with y of s to the left-hand side, add them up, and then I find y of s divided by r of s is G1, G2 divided by 1 plus G1, G2H. Okay? So now if we want to do this without using signal analysis and just using the table we had in the previous slides, we simply combine these two blocks and we write this a big block here, G1 times G2, and then I have G1 times G2 in feedback with H, which from the table I would have G1 G2 divided by 1 plus G1 G2H. So yeah, it's not very difficult to do this if you look at the table. So this is called the closed loop transfer function of system in figure 2. So if you have a feedback system and if you're being asked to write the closed loop transfer function, what we are talking about is basically to put this entire thing into one big block with this transfer function. That is called the closed loop transfer function. All right, now how about doing some examples of simplification of block diagrams? I want to simplify this block diagram. What do you think we should do here? I suggest you to pause the video and try to think about it yourself. Just know that the solution is not, the final solution is unique, but the way to get there is not unique. Okay, so there are many different ways you can simplify this. For example, well, you might say, how about moving G2 here so I can combine it with G1? Or you might say, wait a second, if I move this pickoff point here, then I can simply combine G2 and G3, and then G2 and G3 are in feedback with H2, and then this pickoff point being here means that H1 with this 1 here can be added. So that's another way of simplifying. Somebody else might say, well, actually I want to move G1 here and then combine these summation points. That would be great. I'm going to have 1, 2, 3 summation points. They all would be combined and then a bunch of signals would go in. Okay, so what I have tried to do here is to move G2 here to combine it with G3. So if I move G2 close to G3, what happens is that I need to compensate in the signal that is coming out with dividing it by G3. So if I move this G2 here, then I need to divide this H1 by G3. So then what happens is that I can combine, so this signal here, if I move the pickoff point here, I can combine it with this root with just adding a 1. Whatever I have, I can just add a 1. And then I have a feedback loop here, which I can use the formula to simplify it. Then I just simply multiply G1. Then I have a feedback loop that creates this much larger transfer function. So this is the closed loop transfer function of the entire system. This is another example. These are now positive feedback, and I recommend you to do this example yourself. And this is the final answer solution.